think we're going to get started. Good evening, everyone. Thank you so much for coming. Before I introduce our speaker tonight, I want to remind you that this is an uplift event, and so I have to read the awkward statement. Thank you for attending this Uplift qualifying event. Uplift encourages and supports programs that promote global awareness, interpersonal development, and/or personal wellness. Students are encouraged to snap the QR code, so I was holding it before and Alex has it in the back. So if you're a student and haven't snapped it yet, you can get your chance. But it tracks your attendance and automatically you can be entered into the Uplift prize drawings at the end of the semester. Students are also eligible to win a small prize for attending today, which we will hand out during the Q&A section of this. And your presence matters, so thank you for being here. It is my pleasure to introduce Dr. Alain Brizard. He's a physics professor here at St. Michael's College and chair of the department. He's a returning speaker as part of our St. Michael's College seminar series on topics that impact the world today. Dr. Brizard is originally from Montreal, Canada. He earned his PhD in astrophysics from Princeton University, and after that he did his postdoc in California at Lawrence Berkeley National Laboratory at the University of California, Berkeley. He arrived at St. Michael's in 2000 and was promoted to full professor in 2012. For decades, he has been one of the world's leading theorists in fusion plasma research and its role in developing clean energy. He is the author of over 100 peer-reviewed presentations, including some that have St. Michael's College students as co-authors. And his presentation today will help answer the question, is there a clean energy path to a stable climate future? Welcome and thank you, Dr. Brizard.
Thank you, Liz. Well, welcome everyone. So my talk today will mix energy and climate, and I'll try to connect the two topics and then try to answer the question that is posed by the title of my talk. Is it possible to find a clean energy path to a stable climate? The outline of my talk. First, I'll introduce global temperature as a climate marker, and then introduce the various forms of energy that are used in our modern world, say a few things about the climate footprint of each energy source, and then talk about climate stability, what do we mean by a stable climate, and then I'll present the pros and cons for the case for nuclear energy. And then I'll end my talk tonight by talking about the energy of the future. And this energy of the future needs to be clean and it needs to be plentiful. As a plug for a course I'll be teaching in the spring, so much of the material presented tonight and far more will be presented as part of an environmental science course, ES 312, which is called Energy and Climate Change. So what we're looking at right now is going to be a movie that shows global temperature anomaly from 1880, post-industrial revolution, up to 2021. So the global the anomaly here is how the temperature is this year compared to a previous 10-year average. So we're looking at minute changes in global temperatures. These are temperatures averaged literally over the globe. And if we run the movie, so you're seeing some yellow spots and some red spots. So we're well into the first half of the 20th century, and we can see, of course, some areas that are now progressively becoming more and more red. So the red here is a 2 degrees Celsius above this average temperature. And in 2021 here, you can clearly see that the Arctic region has warmed up significantly. And the Arctic region on Earth essentially plays the role of the canary in the mine. It is telling us that there is something seriously wrong with the temperature on Earth. Once again, on average. Doesn't mean that there are no regions on Earth that are getting colder. But this is an indication that if we use global temperature as a climate marker, there's definitely some evolution of climate on Earth. This is a similar profile showing this temperature anomaly from 1884 to 2021. And you can see here there's a definite pattern involved in the evolution of this temperature anomaly as a function of time. So these are measurements. We have not yet introduced any context, any interpretation of these measurements. So as the first part of this puzzle, the puzzle that is these temperature anomaly profiles, I'm going to introduce the concept of energy. So energy here in our modern world is simply that we use energy conversion from one form of energy to another form of energy as a way to provide us power to do things in our daily lives. So for example, the average daily diet for an adult is 2,500 calories, which overall gives you, in the course of the day, you're able to do 121 watts of power in terms of your daily activities. In addition to supporting your metabolic system. Another interesting fact, a 60-watt light bulb left on all day, it's going to use 1.44 kilowatt hour of electricity. Now, in the US, we do not use the unit of energy, which is the joule. Instead, we use the product of power and time as a means of introducing numbers for energy. So a kilowatt hour is about 3.6 million joules. So it's a lot of energy. But again, a 60-watt light bulb left on all day has spent 1.44 kilowatt hour. A kilowatt hour of electricity costs about 15 cents in the US. So that means that if you leave your light bulb on all day, you've spent less than 20 cents of electricity. So I often tell my students that if you go home for Thanksgiving and you leave your light in your bedroom on all day, and your parents tell you to turn off the lights, do not give them a quarter and tell them to keep the change. That will not go well. On the right-hand side here, we see the various forms of energy that we have in our daily lives. We have chemical energy, we have thermal energy, physical or mechanical energy, electrical energy, and solar energy. So we're looking here at conversions between these forms of energy to power our daily lives. There is a fundamental law of physics that these energy conversions are constrained by the laws of thermodynamics. According to the laws of thermodynamics, you cannot completely convert input energy into work. That's an important law of physics. We have no choice about this. So for example, when you eat food, again, when you eat food, you have input heat energy into your body that allows you to do work, to walk, to do whatever you need to do in your daily lives. And then that input heat coming from the food that you've eaten, not all of it can be converted into work. In fact, most of it, for the human body, about more than 90% of the input energy that you ingested with the food is going to be expelled into the environment. We're a highly inefficient machine. So living beings and machines convert energy, food, and fuel to do work. Not all input energy can be transformed into work, and the output energy, the waste heat, is expelled into the environment. So our mere existence is at the expense of the environment. So when we think about harmony, living harmoniously with the environment, that doesn't mean that we're not having an impact on the environment, but we're able to establish some kind of equilibrium where we are not impacting the environment in a serious way. The sun is the source of all of our energies. Well, almost all, and I'll explain briefly what that is. Unfortunately, my pointer is not working, and so do you have a laser pointer, or because this one is not working? All right, so the sun is coming and is providing us with incident sunlight. That incident sunlight is hitting the top of the atmosphere, and then about 30% of that energy is reflected into space in a process called albedo. So 30% of that energy is reflected. Most of it by the clouds, by the atmosphere, and some of it is also reflected by the surface of the earth. And then some amount of energy is absorbed by the atmosphere and is also stored in water vapor, and about 1% of that input solar energy is used to create winds and water currents. Very small amount of solar energy is converted through photosynthesis for the energy for the plants. And of course, the plants are eaten by animals. And then eons ago, animals that died provide us with a source of fossil fuels. So that's the basic idea here. And because what comes in must come out, about 70% of the energy from the sun escapes into space in the form of infrared radiation. And we'll talk about infrared radiation later on. So we have a complete energy budget. 100% comes in, 30% is immediately reflected, and 70% allows the machinery on Earth to operate. Sometimes the course ES 312 is charts, 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 charts. the idea here is that the students in environmental science must become proficient at reading charts, reading tables, and processing the information in such a way as an environmental scientist, you may then provide important information to policymakers, for example. All right, so you need to be able to process and analyze the data. And the way to do this is by practicing analyzing data. So this is showing the energy consumption in the US in 2021. A quad here is 10 to the power 18 joules. That's a lot of energy. But that is provided on the left here with different sources of energy. So for example, 1.5% of that energy portfolio comes from solar energy. And then you go down, so the first 5 are considered renewable energies. So we see here that if you do a quick math, you have less than 20% of the energy consumed in the US came from renewables. And 32, 10, or 11, and 36 came from fossil fuels. So we're looking here at about 70% of the energy consumed in 2021 came from fossil fuels. So we're going to make the connection between fossil fuel and climate change. We always need to be mindful that if we're going to replace these fossil fuel sources of energy, we need to provide alternatives. We can't say, well, we have to stop using coal as a source of energy. Well, that's going to create a gap, and we need to fill that gap with something that is reasonable to everybody involved. As I mentioned, the laws of thermodynamics tell us that 67% of that energy is expelled into the environment as waste heat. Only 33% is useful, is used to do work, to do whatever we do in our daily lives. So this comes in 5 different categories. First of all, we use energy to produce electricity. So it lights our lights, it allows our computers to function, and so on. So electricity production here, as you can see, is primarily involving coal, natural gas, and some of the renewables. The electricity production then is fed into residential, commercial, and industrial. The difference between industrial and commercial is industrial, you make things, commercial, you sell things. It's as basic as this. Transportation is a huge problem when we look at the solution of climate change with and energy. So most of the transportation here, as you can see, is by using gasoline. A little bit of biodiesel, but it's mostly gasoline. There's a very thin line connected to electricity. So the goal here is to increase the role that electric transportation play in our modern society. Each of the fossil fuel and fuel-based energies have a certain energy content. And here the energy content is written as joule or megajoule per kilogram of fuel. By far, we will see the dirtiest fossil fuel, the one that has the least amount of energy content is coal. You need a lot of coal to match the energy content, for example, of natural gas. Natural gas has almost twice the amount of energy per kilogram that coal has. So we will see here that we are desperately trying to move away from coal as a source used for the production of electricity. And then we have biomass. Hydrogen has a very large amount of energy content. That's because the mass of hydrogen is so small. So it's always, when you look at Vermont as a state, and anything you look at per capita, Vermont is going to be at the top of the list, near the top of the list. The number of Priuses per capita in Vermont is going to be pretty high, right? Because the denominator is small. And then we look at nuclear fuel, nuclear fission, and nuclear fusion. And you can count the number of zeros here. This is not a typo. There's a lot. There's an incredibly high energy density in nuclear fuels because you're tapping into the binding energy of the nucleus. So this is a snapshot provided by our friends at New York Times in 2020. So this is the evolution from 2001 to 2019 of what type of energy was used to produce electricity. So you can see in 2001, 51% of the electricity was produced by burning coal. And then 21% nuclear, and so on. And you can see here there's an evolution. In about 2005, nuclear dropped from second position to third position. You can see natural gas progressively increased its prominence in our energy portfolio, ending in 2019 as providing 38% of the energy production in the US. Coal fell to second place, nuclear in third, and then you can see wind. The yellow here is solar power. So you can see that there's some evolution in how we generate electricity in the US. Let's look locally. This is the similar map for Vermont. So before the closing of the Vermont Yankee nuclear power plant, 76% of the energy, of the electricity produced in Vermont came from nuclear energy. Hydroelectric was 16% and 7% biomass. At the closing of Vermont Yankee, you needed to, of course, replace that energy source with something else. We can see here the ballooning of hydroelectric power as a source of electricity in Vermont. Now, if you know a little bit about the local geography, much of that hydroelectric power came from Quebec. Solar is increasing its footprint in Vermont. You cannot drive anywhere around Vermont without at some point seeing a solar panel farm across the street from here. As you know, the campus has its own solar panel farm. Just to give you an idea that you can go from one state to another and see a very different profile. So for example, New Hampshire, the state next to us, is still predominantly producing electricity with nuclear energy. It has a single power plant and is producing pretty much a constant 60% of its electricity, and then natural gas, biomass, and hydroelectric. So you can get a sense here that So energy is primarily local. If you have access to hydroelectric power locally, you use it. You don't necessarily need to build a nuclear power plant. If you live near the Bay of Fundy in New Brunswick and in Maine, then you have access to tidal power. So you may exploit this. Iceland has geothermal power, a lot of it. So predominantly, Iceland will be producing electricity with geothermal power. With that energy consumption, there is the side effect of producing carbon emissions. By definition here, the renewables produce very little carbon emission during their operation. During the construction phase of a hydro power plant, there will be some carbon emission. If you mine rare metals to build a solar panel, there will be carbon emission. But during the operation itself, solar energy is clean. You can see here almost 34% of the carbon emission is from natural gas, about 21% from coal, and 46% from petroleum. The low number for coal came from our reduced dependence on coal. And then we can see here 32% of the carbon emissions come from electricity production. 37% from transportation. So if you add the two here, you have 70%. So if you're thinking about, let's reduce carbon emission, let's move toward zero carbon emission, then you deal with the elephant in the room: electricity production and transportation. Especially in a country like the US, vast distances. So transportation is dominating the energy portfolio. A few statements about the climate and the social footprint. On the right, we have greenhouse gas emissions from coal, oil, all the way down to solar. You can see here, as soon as you go below biomass, the greenhouse gas emissions from the renewables are quite low. It is often, so nuclear in particular often has the specter of a nuclear accident, like 3 Mile Island, or Chernobyl, or Fukushima. There's the specter of thousands of people dying. What needs to be taken into account that the nuclear energy itself is quite safe. The number of deaths per year is very low compared to mining of coal, the number of fatalities associated with coal mining. The air pollution, the millions of people who die from air pollution, pollutants produced by fossil fuels. So it's important to look at the big picture and not simply focus your attention on nuclear accidents, which, by the way, so 3 Mile Island, American, all right, burgeoning nuclear technology. Chernobyl, absolutely bad design. A nuclear reactor that would not have been built by a physicist. And then Fukushima, keep in mind, this was primarily the result of a tsunami, which then led to repercussions. I think that New Hampshire is pretty safe from tsunamis. All right, so it's always important to keep in context um, the safety of these energy sources. Energy production, electricity. So, and in terms of the amount of carbon dioxide emission. So we're talking about here, the scale of the vertical axis is in billions of tons of carbon dioxide emitted into the atmosphere. And you can see here, so on the left I have, so China produces 32% of the world electricity, and 81% comes from using fossil fuels. And not surprisingly, you see China has a big chunk of the carbon dioxide emission into the atmosphere. You can clearly see here, since the 1950s, there has been a very sharp increase in carbon dioxide emission. So I started with global temperature as a climate marker, and now we're essentially building a case. I'm a lawyer here, and I'm building the case, right? You're the jury, and I'm building the case that there is going to be a connection made between global temperature changes and increased carbon dioxide emissions through our world. So I'm not sure if this is going to work. Let me try this. This is really cool. Yeah, I can't. So if you go to this website, you can click and you have an interactive map. So Quebec is green. It produces about 19 grams of carbon dioxide per kilowatt hour, I think. So it's fairly clean. That's why it's green. Most of this comes from hydroelectric power. France, I hope you can locate France on the map, is also quite green. About 70% of its electricity is produced by nuclear energy. Germany, another task, I hope you know where Germany is, used to have nuclear energy. About 5 years ago, it decided to completely abandon nuclear energy. Now, it's one of the major polluters in Europe. It's nearly 400 grams of carbon dioxide. Its neighbor, Poland, is really dark. You cannot miss it. And it's almost 600 or 700 grams of carbon dioxide. So Germany played a very tricky maneuver. It abandoned nuclear energy, and it's buying nuclear energy from France. It's buying electricity from Poland. You keep the dirty coal, and we're going to benefit from that electricity. So it's really interesting to look behind the numbers. Australia, as you can see on the eastern side, is actually quite dirty. So Australia has a lot of coal supply, and it also has a lot of uranium. So guess which area of Australia is using nuclear energy? Let's now talk about climate stability. So stability here is an important concept. So if someone pushes me to one side, I'm going to adjust so that I stay up. So this is called negative feedback. And you probably do not want to associate negative and feedback together, but negative feedback is good. You have a perturbation and the system responds to reduce the perturbation. That's what negative feedback is. You do not, as a student, to receive negative feedback from your professors. But it should be viewed as negative feedback. Namely, you're doing something wrong, correct it in such a way that you now do something right. So negative and positive feedback are two adversaries that fight for climate. So let's go back to this time we're looking at concentration of carbon dioxide in the atmosphere. So on the left here, we're starting almost 1,000,000 years ago. And you see the elements of a stable climate. You have oscillations, but these oscillations always return to some stable climate. And then near year zero in the Common Era, you see that the carbon dioxide concentration in the atmosphere shoots up. The right panel shows the increase in carbon dioxide from 1950 to essentially the present. That is a sign of an unstable climate. That there is something that is changing in the environment and the system is not able to return to its previous state. All right? So that's positive feedback. Right? So let's see what it... So how does this come about? So what we need to do, in fact, is to look at the connection between the sun and the surface of the earth and the atmosphere. Once again, at the top, we receive energy from the sun. And then a total of 30% is reflected into space, and that is called albedo. The rest of the energy is absorbed by the Earth's surface. So the Earth's surface is getting warmer. Because it is warm, it's emitting infrared radiation. So that infrared radiation is then moving upward. It is now absorbed by the greenhouse gases in the atmosphere. Those greenhouse gases get warmer and start to radiate energy both up and down. And the downward flow of energy from the greenhouse gases in the atmosphere is what provides what is called the greenhouse loop. All right? So if the atmosphere gets warmer, the surface of the Earth gets warmer. If the surface of the Earth gets warmer, the atmosphere gets warmer. And this is, again, a positive feedback loop. I mentioned here that water vapor is a very, very important greenhouse gas. Most of us think of greenhouse gases as carbon dioxide, methane, and nitrous oxide. The elephant in the room, water vapor, is so large that it too plays a role in the greenhouse effect. And for water vapor, it almost automatically participates in a positive feedback. So examples of feedback loops. On the left, I have a negative feedback loop. So let's say that there's an increase in the temperature of Earth, and we're moving counterclockwise. The increase of the surface temperature of the Earth will increase evaporation from the surface of the Earth. That increased evaporation will create more clouds. The increased number of clouds will increase albedo, the reflection of sunlight into space. The increase in albedo will cause less solar radiation absorbed at the surface of the Earth, and now that increase in temperature has been eliminated. All right? Again, negative feedback. On the right, we have a positive feedback loop involving ice cover in the Arctic. So we have an increase in temperature that will decrease the ice cover in the Arctic. A decrease in ice cover will decrease the albedo. A decrease in the albedo will increase surface temperature, and the increased surface temperature will decrease the ice cover. And the cycle repeats until we have what we have currently in the Arctic. We have the almost disappearance of ice during the summer months. So it's possible to navigate in the Arctic Passage freely in the summer. This is a simple model I built for the course. I have surface temperature that depends on only two parameters, albedo and a greenhouse parameter. So the greenhouse effect is a very, very useful effect for us. Without the greenhouse effect, with 30% albedo, the average surface temperature on Earth would be minus 19 degrees Celsius. That's the average, all right? So that would be awfully cold. But because of the greenhouse effect, our average surface temperature is 15 degrees Celsius. So again, that's an average. So equatorial temperatures will be higher, and mid-latitude temperatures will be colder. But that's the average. The curve on the right is the temperature, surface temperature, as a function of the greenhouse gas effect, a little g. So Earth right now has 39% greenhouse effect. That gives us a fairly comfortable average surface temperature. The case of Venus is where the greenhouse gases went nuts. So much of the atmosphere of Venus is methane, carbon dioxide. The greenhouse effect basically went haywire and increased the surface temperature of Venus well beyond what it should be, given its distance to the sun. So the greenhouse effect is important on Earth, but we need to be careful because of positive feedback loops. It's possible for the greenhouse effect to take off, and then suddenly we have a climate that has been destabilized. So let me, my penultimate topic is nuclear energy. I'm going to define what nuclear energy is. I'm going to present pros and cons. And I'm going to compare nuclear energy with renewable energy. I'm not going to waste my time comparing nuclear energy with fossil fuel, because we don't want to get rid of fossil fuel. So nuclear energy here, all of fossil fuel energy comes from breaking chemical bonds. And you create new chemical bonds, and in the process you release energy. And that energy can be used to do work, and so on and so forth. Nuclear energy comes from the binding energy of the nucleus, about a factor of 1,000 to 1,000,000 times larger. There's a lot. It's the highest density of energy almost in the universe. All right? So nuclear energy is a very potent source of energy. So here, for example, a typical nuclear fission reaction, we have a neutron that is absorbed by a nucleus. The nucleus suddenly has too many neutrons inside of it, and it becomes unstable. And the instability of the nucleus is to split apart in a process called nuclear fission. In the process of splitting apart, it produces neutrons. And the name of the game here for a nuclear fission reactor is to slow these neutrons down so that they can be absorbed by nuclear fuel again and perpetuate what is called the nuclear chain reaction. But you want a controlled chain reaction. An uncontrolled chain reaction is called an atomic bomb or a hydrogen bomb. So some of the important issues with nuclear energy. On the right here, we have the binding energy in the nucleus as a function of the atomic mass. So the process of nuclear fusion produces energy if you start with an atom lighter than iron. Iron is at the bottom. So to fuse hydrogen into helium, you're going to release energy. To fuse helium into carbon, you're also going to produce energy. But it turns out slightly less. And as you go down toward the bottom of the curve, the amount of energy that you're producing is going to be less and less and less. For nuclear fission, instead of fusing nuclei together, you're going to get energy out by splitting the nucleus. So if you start with uranium on the right, by splitting it apart, you're going to release energy. Again, energy stored in the binding of the nucleus. So a quick idea here, 1 gram of fusion fuel will give you 30 megawatt hour of electricity. 1 gram of fission fuel will give you about 0.2 megawatt hour of electricity. 1 gram of coal will give you 3 watt hour of electricity. Remember, a 60 watt light bulb, 1 kilowatt hour, about 1 kilowatt hour. All right? So that means that you need to burn about 300 grams of coal in order to get the energy that you need to keep your light bulb on. All right, so that's a lot of coal. Someone is shoveling somewhere. So radiation, nuclear radiation, is always something that people worry about. Again, context is important. So on the left here, you have a pie chart for the exposure to radiation in your daily lives. You can see here about 55% of the nuclear radiation that you are exposed to potentially is because of radon. So if you own a house, you buy a house, you do a radon test, right? Because that is naturally present in the ground. And you want to make sure that you monitor how much radon radiation is in your house. If you have too much, then you have to look at means of changing this. And then the rest of it comes from medical exposure to radiation, consumer products. Interestingly enough, bananas are an important source of radiation, right? So bananas will kill you. No. What I wanted to show on the right is some of the typical exposures of radiation that you are familiar with. So REM here is not a very popular musical group, but it's Röntgen equivalent man. Don't yell at me because this is based on men. All right? So the REM is the equivalent of essentially an X-ray. So a single chest X-ray will give you 2 millirem, so a very small amount of radiation. Dental X-ray, about even less than a chest X-ray. A mammogram is about 40 millirem. A flight from New York to LA, you're going higher in altitude and you're exposed to cosmic radiation. Again, comparable to a chest X-ray. Nobody thinks about this, right? We take the airplane and then we travel and then we say, well, we're exposed to radiation. The yearly US limit for artificial radiation is 0.1 rem. The lowest annual dose of increased lifetime cancer risk is 10 rem, much, much larger. And I think the last one is quite sombering. The typical cancer radiotherapy dose is 200 rem. There's a reason why it affects your body so severely. It's a massive amount of radiation. At a nuclear power plant, the Nuclear Radiation or Regulatory Commission dictates that the radiation at the fence of the nuclear plant must be less than 0.1 rem. All right? So by all accounts, you are getting more radiation in your daily lives than living next to a nuclear power plant. In fact, you're getting less radiation than if you're living next to a coal-fired plant, because of coal has radioactive elements, and these are simply thrown into the environment without any treatment. A very brief design of a nuclear power plant. Except for the nuclear reactor itself, it's the same design as a coal-fired power plant or natural gas, so the point here is to have water so hot that it creates steam. The steam causes a turbine to turn, and the turbine then produces electricity. So that's the connection. On the left, we have the nuclear reactor itself. It has three components. It has the nuclear fuel rods, uranium, for example. It has control rods. The control rods are designed to absorb neutrons. By absorbing the neutrons, they remove all the physical agents that allow the chain reaction to continue. And the third element is the coolant. And the coolant is also playing the role of the moderator. Moderator, not moderator of a debate, but moderator slowing down the neutrons. The neutrons that are produced by fission reactions are too fast. They need to be slowed down before they are absorbed by another uranium nucleus. So the fission neutrons are either slowed and reused or absorbed by the coolant. Absorbing neutron energy in the coolant makes it hotter. And then the hot liquid then can transfer its heat to water, and the water gets hot and produces steam and produces electricity. So the water here in the US, in the Western world, or another liquid, is used both as a moderator and a cooler. The problem with Chernobyl is that the moderator and the coolant were two different medium. The moderator was graphite, the coolant was water. In the Chernobyl accident, there was a bubble that was created in the system. The bubble basically means that there's no longer any coolant, but the graphite is still there. It's still slowing down the neutrons. The reaction took off. That's the cause of Chernobyl. By and large, human error, no doubt. But the physics of the Chernobyl reactor was all wrong. In the US, if you have a bubble, you lose the coolant, but you lose the moderator. The reaction stops. A little bit of the fueling cycle of a nuclear reactor. You start with uranium-238, which is not fissile, and uranium-235, which is fissile. It's the the type of uranium that undergoes nuclear fission. And 3 years later, you still have most of the uranium-238 present, and you've depleted your uranium-235. So that means that you need to shut down the reactor and replenish the uranium-235. So it's a little bit of a cycle, and you can see also that you're producing additional fission products. So that is nominally the nuclear waste that you need to take care of. So nuclear energy versus renewable energies. So I'm here comparing based on 8 different criteria. So renewable energies here will include solar, wind, and hydro. In terms of cost, building a nuclear fission reactor is expensive. Building a solar panel farm or a wind farm, much, much less expensive. And consequently, the advantage goes to renewable energies. Efficiency, energy efficiency, the efficiency with which you convert energy into electricity. On average, for nuclear energy, it's about 40%, 90% in hydro, 30% in wind, and 15% in solar energy. So that means that, let's give this one to nuclear energy. Carbon emission, they're both green. Land use, a nuclear power plant is very small, could definitely fit within the campus of St. Mike's. If you look at a high power output solar farm, it's not going to be the size of the campus. It's going to be much larger. Hydroelectric dams cover large areas. Wind farms also cover large areas. If you travel anywhere in northern New York, you see vast areas of land with windmills. Lifetime, a typical nuclear fission power plant will last between 40 and 60 years, while solar panels, we will soon discover at St. Mike's, they were built essentially 2015. So in about 7 years from now, we're going to have to look at upgrading. The waste, radioactive for nuclear energy. The waste from renewables really come if you build a solar panel. You need to mine rare earth metals. And I don't know if you've ever seen those mines, but there's a lot of toxic chemicals that are released in the process of mining for those rare earth metals. So it's not as clean as you would think. But because it's just merely toxic, I'm going to give that one to renewables. Reliability, nuclear energy is available on demand. And large scale. I always use the example of the production of aluminum. Aluminum is a dominant metal in our daily lives, but the production of aluminum is highly energy intensive. So much so that only a few countries around the world produce aluminum. Canada because of hydroelectric, Brazil because of hydroelectric, China because of hydroelectric. I think you're beginning to see a pattern, right? So you're not going to be able to produce aluminum with wind energy or solar energy. It's too intensive. So we're going to give that one to nuclear. And sustainability here, well, by definition, renewable energy is renewable. So you can, as long as the sun is around, for about 4 to 5 billion years, we're going to be able to use that type of energy. A few notes here. The cost of nuclear energy could be severely reduced by developing what are called small modular reactors. The lifetime of a nuclear reactor being about 2 to 3 times the lifetime of renewable energy power plants, then the cost should be folded into the lifetime. Waste long-term storage is available and feasible, and we should also develop means of processing the nuclear waste. And lastly, sustainability. Right now, the problem with nuclear fission is we're focusing on uranium-235, the fissile part. Some countries around the world, Canada, for example, has developed technology to use uranium-238, which is almost the entire amount of uranium available on Earth. So we have thousands of years available of fuel. And so let me conclude. Fusion energy is another type of nuclear energy. This is, instead of fissioning the nucleus, splitting the atoms, we fuse atoms, in particular isotopes of hydrogen. The reaction products, helium, are completely non-radioactive. Let me start at the bottom. Fission is easy, fusion is hard. We're trying to build a star on Earth. Not an easy task. Nuclear fusion has the highest energy density almost in the universe. The fuel is water. We have several billion years worth of fuel on Earth. There's no radioactive waste, and the fusion reaction stops if anything goes wrong. Research at the moment into nuclear fusion energy is done by international projects on the left and private companies on the right. There's tremendous effort all around the world in developing nuclear fusion energy. So let me conclude. So we need to continue investing in clean renewable energies. So by simply cutting electricity production by fossil fuel and turning our attention to electricity production by nuclear and renewables, we've cut already 32% of carbon emission. We need to consider technologies for carbon sequestration. We need to support research in nuclear fission energy, work on nuclear waste management and processing, and develop more advanced nuclear fission reactors. And the goal here, the long-term goal, is to develop nuclear fusion. And that's it. So that's the path to a clean energy, stable environment. Developing a portfolio of renewable and nuclear energy. Thank you for your attention. I don't know if you wanted to proceed with questions. Or not.
We can proceed with questions. And for the students that are here, there's some prizes if you ask questions.
All right, well, thank you. Oh, once again.
We have a couple.
Yes.
You talked about albedo on Earth, and recently there was a change in policy where international ships had to stop using sulfur dioxide or trioxide in their fuel, which caused the albedo of the North Atlantic Ocean to drop. What do you think of climate solutions where we kind of geoengineer the solution with, for example, the release of sulfur into the atmosphere?
Well, sulfur dioxide.
Well, I don't remember.
Yeah, um, it's clear that because albedo, as you saw, is part of a positive feedback loop and a negative feedback loop. So albedo is a crucial element in climate. So of course, you need to do, so once you decide to adopt a particular transportation mean, right? So you need to look at the impact it might have on albedo. A few years ago, there was this conspiracy theory of contrails. You know what contrails are? Right, so airplane traveling in the sky and leaving a track of water vapor condensation. So a lot of people were saying, aha, that's responsible for climate change, contrails. And if you look at it carefully, you see that it plays absolutely no role. It's just too insignificant. Now, of course, if everybody decides to fly a big airplane and we cover the entire atmosphere with contrails, then that's different. So in your scenario here, so you need to look more closely at and model how the transportation process, what impact it would have on albedo.
We can do another question about kind of think about what is your view on the likelihood or like the future of making nuclear fusion cost effective? It's so many startups and in the venture capital space are just pushing it so hard, which only could tell me that they kind of believe it's possible in the near future. But then it's so cost intensive, right? So it seemed that the government needs to kind of subsidize or help out. So what's your view on that?
So so on the right, we have all the companies around the world that are developing means of producing nuclear fusion energy. And I have no doubt that once a first nuclear fusion reactor is built, the cost of electricity will be, a wild guess here, $50 per kilowatt hour compared to 15 cents, right? So everybody, any reasonable person will say, forget it. I'm not going to buy electricity from a nuclear fusion reactor. The cost of electricity is going to jump through the roof. Now, wait another 50 years. Then suddenly the electricity produced by fossil fuel will go up, right? And by developing nuclear fusion, the cost of electricity will go down. At some point, the two curves will meet. 100 years, 200 years, I don't know. But if we delay the development of nuclear fusion, that delays the curve of nuclear fusion. And at some point, the cost of fossil fuel-based electricity becomes $2, $10, $20 a kilowatt hour. Then we say, oh my God, we need to develop nuclear fusion. It's too late, right? We're trying to build a star on Earth. That takes time. We've been trying to build a nuclear fusion reactor since the late 50s. It takes time. The joke is often that nuclear fusion is always going to be 20 years in the future. That's no longer the case. It's no longer a joke. We have massive investments. The brightest minds actively working on a way to produce energy through nuclear fusion. It will happen. And I venture a guess it will happen in my lifetime. And I'm old. It will definitely happen in your lifetime.
I think you said that fusion was more powerful by a factor of 3, I think, than fission. And just judging by how fission hasn't exactly exploded, being used all over because we're still relying on fossil fuels. What do you think is going to make fusion take over so much more rapidly if fission hasn't done that yet, and it is so much more powerful?
So you may have seen Back to the Future, right? So Doc comes back from the future in a DeLorean, and in the back of the DeLorean, there's a Mr. Fusion in the back, right? I don't think we will ever see a Mr. Fusion, right? So nuclear fusion will still be predominantly used to produce electricity. We're not going to use nuclear fusion as a means of transportation or, but electricity production then will fill the gaps in residential and commercial and industrial. Transportation, we need to shift our attention toward electric transportation. All right, and you might ask, where's the electricity coming from? It's going to come from either renewable energy or nuclear fusion. It's important to keep in mind that nuclear fusion is not going to be a solution that fits all. Norway is still going to use hydroelectric power. Quebec is still going to use hydroelectric power. We don't need nuclear power, right? So energy is local, but there are many countries around the world that do not have access to hydroelectric, or countries like Germany where wind power is useful, but again, you need reliable energy supply. And nuclear fission is a short-term solution. Long-term solution, I'm convinced, is nuclear fusion. 100 years, 200 years, but at some point it needs to be developed. If you wait too long, Sally Ride was the first American woman in space. She was a plasma physicist. She was an expert in my field, and she was asked at a conference, she was asked, how easy would it be to return to the moon? And we're seeing this right now. Would be extremely expensive. Would be extremely expensive. You think, well, we've been to the moon before. So what's the problem? We no longer have the plants that build a Saturn V rocket. The engineers and the scientists that built those rockets have long since died or retired. There's no expertise. The young engineers now do not have the expertise of building these extremely powerful rockets. All right, so we need to relearn a lot of things. And so going back to the moon is not going to be cheap. The fact that we've done it before is almost irrelevant. So if we need to develop nuclear fusion now, we need to continue developing nuclear fusion and continue decreasing the cost of electricity. We are studying a state of matter, the plasma state, which is now converted into what is called the burning plasma state. The only places in the universe where that state occurs is in the core of stars. Not a very comfortable location for a lab. All right, so we need to explore the burning plasma state in order to develop nuclear fusion energy. It's very, very difficult. But the fact that it's difficult does not mean that we cannot do it. In fact, we know that it's going to work. The key point here becomes a political issue, a social issue. Are we willing to invest money and time in developing a technology that you will not see the fruits of for a long period of time? Hopefully before I die. All right?
Any other questions? Seeing none, Please give another warm round of applause to Dr. Brizard. Thank you very much.